Thanks, Ben. Thanks, Noel. Like Michelle, like Noel, I have not done one of these Zooms in a while, so I'm going to try and share content. Let's see if this works.
We can see it.
Thumbs up? Are we good?
Yeah.
Wow. That was the smoothest. Most of the times I had given Zoom talks and I had to do this, there was often like a hitch. And so I'm really happy I can't believe it. Look at this. This is fantastic. All right, great. So I'll get started. Great to see all of you. Thanks for spending Friday with me in this lovely community that Noel and Ben have got started. Supported by AIM, I should give a shout out to Michelle and AIM. Some of the research I will speak about was born of a square that is complete. So the 3 years are done, and now I'm in my second square. And so it's a really fantastic program. I strongly recommend you find out more about AIM and get involved. Okay, so I'm going to talk about a few of my favorite things. Ben mentioned them. There's actually a soundtrack to this talk. I want to try and share my slides with you. Give me one sec. This should, how am I going to do this? Just give me one sec, sorry. File. I thought we can just share slides. Is that through the chat or is it through something else?
Are you trying to share the file?
Yeah, just the slides.
So I think if you drag and drop the file into the chat or at the bottom
Okay.
of the chat next to the emoji, there's like a file thing and you can upload from your computer.
Okay, let me see. Next to the emoji thing, there's a file.
Like the
Yeah. So now
yeah.
I'm clicking on my computer, but it's sort of
Oh,
disabled.
it's not showing
I have
that.
Dropbox, Microsoft OneDrive, Google Drive, all of those options, but my computer is somehow
If you
missing.
email it to me quickly, then I'll try to drop it in the chat while you go ahead. Is that,
Perfect. Let me do
yeah,
that.
okay.
Great.
Yeah. And question in the chat, you said it has a soundtrack?
Yeah. So if you have the slides have links, and the links are in this color, like
Okay.
as written on the main slide. And if you click on my favorite things, you will start hearing the soundtrack. So it takes you to a YouTube video of one of my favorite versions of My Favorite Things by John Coltrane. And so I thought it would be nice. So if you want to like say, oh my God, this talk is so boring, trust me, John Coltrane will not bore you. So there's your out. Okay, so let's keep going. All of this work, as I said, is joint and done with various combinations of Mariusz Urbanski and Lior Fishman. Here are a couple of our papers that I might talk about. And just to put this in context, Mariusz was David and my PhD advisor. David and I started together and we ended together at getting PhDs with Mariusz in 2012. And Lior joined our department, I think, in maybe a year or two before we graduated. and he started working with us on a bunch of projects. And being nurtured by Mariusz has been a huge blessing for me. And I think this is really important for young mathematicians. If you can find people who nurture you and inspire you to work on very challenging stuff, you should find them and stick to them. And so Mariusz is definitely one of these people in my lives. So I'll start thanking my teachers. So here's a poem by Lao Tzu from the Tao Te Ching. This is a translation by the amazing writer Ursula Le Guin. It says, good people teach people who aren't good yet. The less good are the makings of the good. So far, so good. Anyone who doesn't respect a teacher or cherish a student may be clever, but has gone astray. And then there's the most mysterious line of this poem. There's a deep mystery here. So there's a couple of links to references. If you're not used to thinking about things like Hausdorff dimension or thinking about things like conformal iterated function systems, I would say the best, let me see if I can start using, one of these is a highlighter, but I'm not sure which one. Let's try this. Oh, wow, great. So the last one, which is Urbanski, Roy Monday's non-invertible dynamical systems, I think that's what it's called. That's a new 3-volume work that Mariusz has written with 2 of his collaborators, Mario Roy and Sarah Mundy. And it's a fantastic set of books. It'll have any definitions in my talk that you're like, oh, wait, I want to hear a bit more about that. It's a great reference. If you want something really short, so this last one is really comprehensive. A short one would be Mark Polycott's Fractals and Dimension Theory Notes. It's about, I don't know, 80 pages, 90 pages. It's really well written. That's also a good reference to have. Okay, so my first teacher as an undergraduate at St. Andrews in 2003, it was a 3-year degree, and in my second year, I met him. His name was Bernd Stratman. He sadly passed away a few years ago, and I'd kind of like to dedicate this talk to him. And he got me thinking about 3 topics: continued fractions, Fuchsian groups, and how they interact with the rest of mathematics. And so there's these 2 really amazing little slim volumes, Continued Fractions and Fuchsian Groups, that you should read. And then if you like it, if you like the flavor of what's going on, I cannot recommend strongly enough what Bernd used to call the Grün book, which is the green book, the Ergodic Theory, Symbolic Dynamics, and Hyperbolic Spaces. So if you've not heard of this book, trust me, it will surprise you. You will love this book. It's a bunch of different chapters, and each chapter is a set of amazing lecture notes. And a lot of what I'll talk about is got to do with problems that Bernd introduced me to back in 2003, and it's now just past 2023. So, it takes time to, Michelle was talking about how sometimes you can work on projects that take 3 years. In my case, I'm very slow, and so I take more than 20 usually. So let's get started with a favorite conformal iterated function system. I'm going to start with a definition by example. There'll probably be very few definitions in this talk. So this picture is a picture of the map 1 over x mod 1. X maps to 1 over x mod 1. So you take the hyperbola, and then you chop it up and slide it down so that it fits inside the unit interval. And then each of these branches has an inverse branch. And so when you reflect in the line y equals x, you can see the inverse branches of this Gauss map. Those inverse branches are going to form the generators of our conformal iterated function system. So for example, you might be familiar with the Cantor set. So the Cantor set, you start with maybe the unit interval, and then you've got two generators that split up the unit interval via contractions to small copies of the big interval that are, in the case of the middle third Cantor set, they're 1/3 the size of the original space you started with. In the case of, so these objects like Cantor sets or Cantor spaces are topologically like 0, 1 to the n or 2 to the n. The kind of fractals we're going to study today are going to include Cantor spaces like 2 to the n, but they're also going to include Baire spaces. So Baire spaces are, instead of having two generators in your IFS, you're going to have countably many generators. And so now the picture is going to be something a little more complicated. So it's going to be, okay, we start with the unit interval, but then instead of chopping it into two pieces, we'll chop it into countably many pieces. Okay, and then iterate. And then, there's this nesting process that you all are familiar with when you studied, like, say, the Cantor set construction. And at the end, at the bottom of this nested sequence of sets, you have a very nice fractal. And one of the things we'll be studying in this lecture is, what can we say about the Hausdorff dimension of this fractal? Okay, so what are the maps that you just saw pictures of? So for every positive integer I, let's define the Mobius map. Gi of x is 1 over I plus x. Okay, so for example, two famous ones could be just these two very simple rational maps. So there's G1, G2. There's countably many of these. And each of these GIs, as the picture told you, is an inverse branch of the Gauss map. Okay, so there is the map 1 over x mod 1. And for any set of integers, you're picking a bunch of these branches, the collection of maps, GI, can be referred to as a Gauss conformal iterated function system, or a Gauss CIFS. Okay, so you can see there's a lot of choices here. And if you allow the entire set of positive integers, then you get the Gauss, or the Gauss CIFS, instead of a particular Gauss CIFS. Okay. So we talked about continued fractions, and this getting me into hyperbolic geometry, etc., and dynamics. So these Gauss maps are intimately related to continued fraction expansions. So if you take a finite string, omega, of n positive integers, and then you form the composition, G omega, of the corresponding Mobius maps. If you write this out, you'll see, because the maps are 1 over 1 plus ix, you start getting the continued fraction expansion being developed, as you can see here. Sorry. All right, so for example, the orbit of 0 of G omega of G of omega is exactly the continued fraction with the digits omega 0, omega 1, up to omega n minus 1. By the way, this is just notation for that continued fraction. Okay. So the limit set, that fractal that's sitting underneath, is simply, as you've did for the Cantor set, the intersections of all these intervals at every stage, right? So the final product at the end, we could call it Fi. And so for every set I, every set of generators you pick, Fi generates this fractal. And in this simple case where everything's maps of the unit interval, of course, this sits inside 0, 1. Okay. In terms of just elementary calculus or analysis, Fi is just the set of all irrational numbers in the unit interval whose continued fraction entries all lie in the set I that you picked. Okay, and I'm sure you're very comfortable with this, but like just interrupt me with questions. I'm sometimes looking up at you, but then I'm looking down at the iPad, so I can't see you. So just shout out, just unmute and say something if something doesn't make sense. All right. So now these fractals are large in some sense, but they're also small in some sense. So if you sort of look at them with the wrong magnifying glass, so if you look at them like say with Lebesgue measure, one-dimensional Lebesgue measure, they'll be invisible. So Lebesgue measure is not a good enough magnifying glass or a tool to be able to capture how large these sets are. And so this gentleman, who is one of my mathematical heroes, Felix Hausdorff, or as he was also known as Paul Mongret. By the way, there's a link here that I strongly recommend you investigate later to find out more about Felix Hausdorff's double life. He was also a poet, a dramatist. He wrote plays. He was a music critic. He wrote philosophy. And his complete works are currently under, what's it called? Being published. And so I think, I don't know, 6 or 7 volumes are out already. But this article that is linked to in my slides will give you a brief snapshot that appeared in the Math Intelligencer about his double life. It's very fascinating if you don't know about Felix Hausdorff. So anyway, all my papers, I'll just mention this as a personal comment. Every paper I think I've worked on, or every project I've worked on, in some sense is a footnote to Felix Hausdorff's ideas. Okay, so Hausdorff dimension is this tool for studying intricate fractal sets that are invisible to Lebesgue measure. And morally, it's a way of measuring the size of such sets so that it matches up. The dimension of a smooth manifold is equal to the topological dimension of that manifold. But it also does better than that. So there's a formal definition that I'm not going to read out. Again, we've only got an hour or so. So for definitions, you've got to look at the references or reach out to me for help. Oh, and that's another thing. You can always email me about questions you have on anything. So you got this Hausdorff dimension idea, and you've got these fractals, Fi. Okay, so the first person who put these together, well, I shouldn't say the first, because Hausdorff himself did do this. And Jarnik was also not the only one interested in thinking about Hausdorff dimension of intricate sets that came from number theory. Besikovich also did. Abraham Besikovich. And Jarnik was one of the first people who did this. And he had an amazing paper where he studied the Hausdorff dimension of the set of all irrationals where the continued fraction entries have, oh, I should have just said entries. The old-fashioned term for entries were partial quotients. So these are just the digits, are all less than equal to n. Okay, so in this case, I is just the set of the first n positive integers. So in 1928, Yarnik, in his seminal paper, established the following bounds for the Hausdorff dimension of f less than equal to n. Okay. The next person who had a great result about such sets was Jack Good, who is pictured here with his father. And I wanted, again, it's Friday, you're tired, let's do some story time. So this is from an interview of Jack Good, reminiscing about his days when he played with continued fractions for the first time. So Good is talking about when I was nearly 10, I was in bed with diphtheria. I worked on trying to extract the square root of 2. Now, if none of you have done this, I strongly recommend you try and do this, okay? Without a computer, try and extract the square root of 2 in as many ways as you can. It's a really fun exercise. And if you have to fall sick, go ahead. Don't get something as serious as diphtheria, maybe. So his interviewer asked, do you think the diphtheria helped? And Good answered, well, it gave me a lot of time. And some of the best work by scientists occurred because they were away from the madding crowd. And I thought this was really funny, especially during the pandemic, when I was thinking about some of this stuff. So anyway, Good goes on to describe some of this work I'm going to tell you about. So he talks about his advisors, Besikovich and Hardy. And he said that at that time, what I liked most was the amazing formulas such as those of Ramanujan. Again, if you don't know who Ramanujan is, please find out. Another very singular, mysterious mathematician, one of my mathematical heroes, just like Hausdorff is. And so Besikovich suggested that I might investigate the fractional dimensions of sets of simple continued fractions defined in a simple manner. And he's very humble about this, but he says my research in this area was awarded a Smith Prize. And you can look up the winners of the Smith Prize. They include people like Turing, almost anyone who left Cambridge with an amazing math career had won the Smith Prize. And so he won the Smith Prize, and I'll show you what his Smith Prize essay contained in a second. It's also interesting that the minute he graduated, so this was his, his kind of thesis problem, and then he graduates, he gets the Smith Prize, but then guess what? Look at the time, it's about 3741. He, along with Turing a few years before him, were immediately whisked away to Bletchley Park, where they joined the war effort in trying to be code breakers and help the Allies win World War II. So he sort of had this amazing thing with continued fractions. Then he was whisked away by the war. But then he came back, and in this interview, which is towards the end of his life, he was about 70, I think, when he was writing, when he gave this interview, he talked about how he came back to this continued fraction problem in no less than about 15 papers over the course of his life. And it's the same set, okay? So he was kind of obsessed with this problem. And so I'm going to skip this just for time and tell you what he proved. So instead of looking at f less than equal to n, which Yarnik did, Good instead focused on f greater than equal to n. So you remember this distinction I talked about between the Cantor space and the Baire space. The Cantor space you should think of as a compact metric space. And the Baire space you should, wait, why is this? Something is, can you hear me?
We can hear.
Okay. I'm writing stuff on the slides and they're not showing up. So I'm not sure.
Is it notability?
Yes.
Maybe just like come out of it and bring it back up. Yeah.
Yeah. Actually, it wasn't, because Notability is still active. I have to rejoin Zoom. I'm really sorry
Okay.
about this. Um,
I'm just gonna say I've been enjoying all of the pictures of all of the people. So,
Thank you. That's a trick I learned from Mark Polycott. I remember being a grad student and I was in Warwick, um, and I remember going to one of Mark's talks. This is one of the first times I met Mark, and I just loved his talk. It was this seamless blend of mathematics and human beings and the world around us. So,
he does give really good talks.
oh, I love Mark's talks. I'm glad you're enjoying the pictures. They're not as good as Mark's, but I'm trying. Okay, is this? Yes, we're back. Let's see, do it
Um,
again. Yes.
yes.
So as opposed to Yarnick's set, f less than equal to n, Good was looking at f greater than equal to n. Okay, so as opposed to a IFS with n generators, Good was looking at an IFS with countably infinitely many generators. So this is going to be a little harder. I was saying that when you think of a Cantor space, you should think of a compact metric space. When you think of the Baire space, you should think of a complete separable metrizable space. Okay. In some sense, every such space is a quotient of either the Cantor space or the Baire space, respectively. So if you like things like, I don't know, the unit interval or S1, or if you like things like the real line, then you're in good company. They're just fractals. So this is what Good proved. And this was one of the major results in his Smith Prize essay. He proved similar bounds like Yarnick had, but for now the Hausdorff dimension of f greater than equal to n. Okay. So my comment down here is that Good's results took a lot of effort to improve. He himself tried to improve them, but he couldn't make major improvements. The first major improvements after 1941 came due to Ramharder and Cusick in the late 70s and early 80s. And then finally, the best result was due to Jerisch Kesselbaumer in 2010. And I've got their result down at the bottom of the screen. Okay. So this slide is pretty much of what was known about f greater than equal to n. Okay, so let's go back to f less than equal to n. Yarnick had a student who was very famous called Yaroslav Kurzweil. You might have heard of Kurzweil as one of the inventors of the Kurzweil-Henstock integral, which sort of generalizes the Riemann integral in such a way that you don't actually need Lebesgue measures. So usually when we were in school, you probably had an analysis teacher tell you that, oh, the Riemann integral is great, but it's not good enough. We need Lebesgue measure, and then we need Hausdorff measure. And that story is great. But what they don't tell you is that Henstock and Kurzweil actually came up with some way of redeeming Riemann's integral in such a way that it can actually extend Lebesgue measure. If you want a book that tells you about this, I teach real analysis here at my college out of Bartle. And so Bartle has a book called Real Analysis, and that explains this construction. Okay. So Kurzweil, under Yarnick's supervision, improved Yarnick's bounds, and he got rid of some of those logs. and I just have a little comment here. If some of you are like, well, I'm not really interested in one-dimensional stuff, there's a higher dimensional story where instead of approximating real numbers, you are approximating matrices. So you could think of real numbers as one-by-one matrices, of course. And so there's a higher dimensional generalization of this result of Kurzweil due to my brilliant collaborator, David Simmons. And in the higher dimensional case, nothing of all the extensions I will tell you about in this talk are known. Okay, so if you really want a challenge, then try and improve David's paper, where he has a result that extends Kurzweil's result to all dimensions. All right, so that was 1951. And then the next improvement came several years later in 1992, when Doug Hensley produced the following asymptotic formula for the Hausdorff dimension of f less than equal to n. So he, in particular, you saw the 1 over n in the previous slide. He, in particular, worked out a couple of terms and a couple of very interesting coefficients. So I started the talk by telling you I dedicated it to Bernd Stratmann, my teacher, who introduced me to continued fractions and hyperbolic geometry. And this was a paper that Bernd gave me, and I really struggled with understanding it. But he gave it to me to see whether I would find it interesting. And sure enough, when I saw these numbers like 6 over pi squared and 72 over pi to the fourth, I was very interested and intrigued. I'd never seen such numbers appear in discussions of Hausdorff dimension. And so, one of the things we would like, talking about during mathematical tea was, what's the next term? Can we work out what comes after this? Or is there a little O term? Or, things to chat about over tea. And that was back in 2003, and it's now 2024. And yes, we can tell you what comes after. So now let's move into the present. So with these brilliant collaborators of mine, we were actually able to find the complete asymptotic expansion for f less than equal to n. It's right here. So remember, this is the Yarnik story. And of course, you're going to want to know what are these CIJs? Do you recover the CIJs that Hensley got, or was there a problem there? And the answer is yes, we have a closed form expression for all the coefficients of the form Ci comma I minus 1 in that formula above, okay? And so the 6 over pi squared and that pi to the fourth term, they're all reciprocal. You take zeta of 2, you take its reciprocal, and then you take ith powers of it. So it's kind of still very mysterious to me where these coefficients come from. Now, the other coefficients don't have, or at least we don't know how to get closed formulas for them, but they should be computable. So if you read our paper and you're interested, you should try and be able to compute these CIJs. And of course, this is just one example. So really, there's a lot of playground here. You could do several things. Okay, my screen broadcasting has stopped again. I now know what to do. Really sorry about this.
No worries. Are you joined like separately from your tablet, right?
Yeah.
Yeah, okay. No, that's the way it usually works best for me, but some days it's not
Yeah.
good.
And I think it might be because of the Wi-Fi, because the desktop where you're seeing me waving into that camera, that's like wired, whereas
Okay.
iPad is Wi-Fi, and so I think that could be a problem. We're in a very old building that needs to be replaced, but continuously misses the budget. So here comes CI minus 1. All right. Now, on the other side, if we go back to good story, right? This is what we get. So this is how you improve good. It isn't quite surprising that it's hard to make improvements to this. But I hope when you first see this, you might be like, oh my God, what the hell? What is this? And I did too. Couldn't believe it as it was expanding. But I want to impress upon you that don't be worried about this, because I'll show you the method how you could get this formula. And you literally could do this with very, very little technology. So it's something that I'm going to show you all the ingredients and how you can get these asymptotic expansions. And then hopefully you'll be inspired to play with some variations on these problems. So again, these coefficients are computable, but we don't know how to get closed form expressions for any of them. Okay. So at the heart of both those theorems I just told you about is a purely functional analytic theorem, which we could call a perturbation theorem, which I'm going to describe to you next. Okay, so we've got a Banach space, B, and vectors in the Banach space will be referred to as F. Maybe I'll pick a color. Its dual space will be B star, and I will use, letters like sigma for elements of the dual, and L of B will be all bounded linear operators on the Banach space, and so I'll use things like capital L for elements of L of B. So if you really want to just break this down into linear algebra terms, you should think of L as being a square matrix, and you should think of F and sigma being column and row vectors. That's all it is. Okay, so once you've got that, then things like sigma F make sense. So sigma of F should be a scalar, and in this case, you just multiply sigma and F and to get a scalar. F sigma, on the other hand, would give you, so this would be maybe an inner product in terms of linear algebra. This might be an outer product. So if you do F sigma, you get a square matrix, and so on. So that's the notation. And we'll be talking about right and left fixed points. So F, remember, is a column vector, so it acts on the right. And so a right fixed point of L is something that satisfies LF equals F. And a left fixed point of L is something that satisfies sigma L equals sigma. Okay. So I'm just looking at the time. I might skip this. I might skip parts of this proof. So here's the setup. We have the following objects. So you've got a right fixed point for L. You've got a right fixed point for another operator L prime. And we're interested in the perturbation. So we're interested in the difference delta between L and L prime. And you know something more about L. You know that L has a left fixed point. And then you need a sort of a normalization condition that says that mu of G is not equal to 0. Okay, so it's not disappearing. So it's a scalar we can scale by, we can divide by it, we can normalize by it. And so we're going to use that mu G not equal to 0 to define R, which is going to be L minus CG mu, where C is 1 over mu G. So we're wanting to form the Neumann series of R, so this is like 1 over 1 minus R. And so to do that, we're going to assume that the spectral radius of R is less than 1. So that Q is well defined. And then there's 3 simple observations, just trust me about them. The first one is a very simple fact that 1 minus F sigma is invertible if and only if sigma F is not equal to the scalar 1. It's a very cute little linear algebra fact. The other one is that because, so this is the first fact. The next fact is that because G is a right fixed point of L, we get that G is also a right fixed point of Q up here, okay? Similarly, since mu is a left fixed point of L, you get that mu is a left fixed point of Q. Okay. All right. Now, we also want to form the Neumann series for delta plus R. And so to do that, we're going to make another assumption. We're going to assume back, undo. Okay, never mind. Sorry. We're going to assume something like we had up here for the spectral radius of R being less than 1. We're going to have a condition that allows us to define the Neumann series delta plus R raised to the n. Okay, so that's again 1 over 1 minus delta plus R. So the point of this, of forming A, is that now we have mu of A times 1 minus L prime equaling 0. I'm not going to go over the proof, but the proof follows from this first observation up here. Okay, so it's a pretty simple linear algebraic proof. And now we've got this equation, mu A of 1 minus L prime equaling 0. I want to turn it into a scalar equation. And so I'm going to multiply both sides of this equation by G. G, remember, was the right fixed point of L. So I get now, instead of an operator equation, I get a scalar equation up there. And really, the heart of our method is that scalar equation. Getting from here down to the end of the proof is just rewriting this equation so that it looks nicer. Okay, there's nothing else happening here conceptually. So, so you've got that equation, and I just want you to trust me because of time that it transforms using the other 2 observations we had, plus this new observation, number 4, that you can rewrite it as this scalar equation right here. Okay, so that was very messy. Let's collect it all together and write it down as a theorem. So say you have these 2 operators L and L prime in L of B. They're bounded linear operators on a Banach space B. They have right fixed points G and G prime, and mu is a left fixed point of L. And again, we assume that mu G is not equal to 0. You don't need to assume both are not equal to 0, but any one is enough. And then we defined R. Remember, R was L minus CG mu, and we wanted to form the Neumann series of R, so we assumed that the spectral radius of R is less than 1. Then we formed the Neumann series Q, and then the perturbation delta. And if you remembered from from the previous slides, this condition was there so that you could define the Neumann series of delta plus R. And so if you assume that condition is true, then you get our scalar equation. Okay. And this scalar equation, the heart of our results is that this scalar equation, so the Hausdorff dimension is hiding in here. And so if you have an equation and you've got a variable that you want to solve for, and it's a complicated equation, what do? You use the implicit function theorem. And if you try using the implicit function theorem to solving for that variable, you might find that it's taking a lot of time. And to speed things up, you use another classical tool known as the Euler-Maclaurin summation formula. Okay, so let's bring in the Hausdorff dimension now. How are we going to use this perturbation result to form these asymptotic expansions? So let's form what are called various things. You can, in thermodynamic formalism language, this is often called the Ruel operator or the Meyer operator or the transfer operator. Well, even before thermodynamic formalism was a phrase, this operator was actually studied by Kuzmin and Versing. And so I like calling it the Gauss-Kuzmin-Versing operator. So that's a very famous operator. If you've studied anything about the ergodic theory of continued fractions, you will have seen that operator. And then there's this other operator, Ln, where you're going to notice that the Hausdorff dimension of f less than equal to n is embedded in there, right? So that's, for example, one of the quantities we are interested in estimating. So this L operator, the GKW operator, it fixes a positive function. You could call it a density, and its dual fixes Lebesgue measure. We've normalized things. In case you've seen continued fractions in other settings, sometimes G will be written with an ln of 2 in it in the denominator. But if you normalize, you don't need to think about that ln of 2. And the definition that delta n is the Hausdorff dimension of f less than equal to n can be encoded by the assertion that the spectral radius of ln, the second operator here, is 1. And again, that's equivalent to the assertion that ln fixes a positive function gn, a positive density, and the dual ln star fixes a positive measure mu n. So now what's the proof strategy for finding those asymptotic expansions? You apply the perturbation theorem with L being the Gauss-Kuzmin-Versing operator, and you let L prime be Ln. So then when you look at this equation, remember L prime has delta n hiding inside it. So there's a delta n in here, right? So capital, I shouldn't, this sounds terrible. Too many deltas. Capital delta is L minus L prime, but delta n is a little delta, and that's the Hausdorff dimension. And so you use, as I was saying, the implicit function theorem and Euler-Maclaurin, and you get this. Same idea works for f greater than equal to n. You just have to be a little careful about picking L and L prime. So L prime stays the same, but there's some changes, which I'm going to skip. Okay. So what else can we do apart from these two sets? I mean, of course, those two sets were very interesting. I tried to give you a history of several results which people were trying to prove about them before we got the complete asymptotic expansions. It turns out that our method, surprisingly, also gives convergent series expansions for the Hausdorff dimensions of such sets. Okay, so instead of an asymptotic expansion with a capital O at the end. So let me show you a fun example. And again, this is meant to make you say, oh, wow, if they can do Fibonacci numbers, maybe we could do fill in the blanks. So let's say delta n denotes the Hausdorff dimension of the numbers whose continued fraction entries are now not 1, 2, 3, 4 up to n, but the first n Fibonacci numbers. Okay, so your alphabet now is not all natural numbers and you're looking at the first n. Your alphabet now is the Fibonacci numbers. Okay, so your entries of your continued fraction will only have the first n Fibonacci numbers in them. Okay, and again, let delta be the limit. So delta is all the Hausdorff dimension of the set of all irrationals whose entries are Fibonacci numbers. So then what happens is you get convergent series expansions for the Hausdorff dimension delta n. So there is no n. This is a precise formula, which I think is also very surprising. We certainly had not seen such formulas in the 100 years since Hausdorff dimension of fractals has been studied. So it was kind of surprising and cool for us to see this. I also want to throw in some history here. I'm really sorry, Noel, I don't have pictures of Virahanka, Gopala, and Hemachandra, but I'm going to work on it. It's kind of hard to find pictures of mathematicians who lived in very hot, humid climates back in the day. Very hard to preserve such pictures. And so there's, of course, artists' impressions of these people, but it's hard to find good pictures. And anyway, my little plug here is check out this paper by P. Singh about how the Fibonacci numbers showed up without thinking about rabbits in several other areas by these mathematicians, Virahanka, Gopala, Hemachandra. And that's just a partial list. There's even more. They weren't thinking, in case you're wondering, some of them were not thinking about rabbits, but what they were thinking about was all writing was done in poetry. And so there was lots of studies about meter rhythm, an area called prosody. And so it's now called prosody in English. And so they were basically beatboxers and rappers, like really good ones. And they had like incredible algorithms to tell you all possible beats within a certain time. And that's how they came up with the Fibonacci numbers. Okay, so what is there for you to play with? So try and first of all, really understand. I mean, I just gave you a very terrible, messy sketch, but really understand that perturbation theorem. And then study some thermodynamic formalism, so you know a little bit about transfer operators, and then use this perturbation theorem and apply it to wherever you have a transfer operator. Okay, so that's the big takeaway. There's lots of directions you could go with that. For example, the kind of systems we were studying are called iterated function systems. They grow up and they become graph-directed Markov systems. And again, that first book that I pointed at by Mariusz Urbanski, Mundy, Roy will tell you what those are. So you could try and extend this from an iterated function system to a graph-directed Markov system. You could, so these f less than equal to n sets are related to a hot topic in dynamics now known as open dynamical systems. So pick your favorite open dynamical system in whatever dimension you want. I would suggest starting in 1 and 2 and try and get asymptotic expansions for what open dynamicists are interested in. So things like survival rates, Hausdorff dimension of survival sets. So yeah, I mean, the very quick summary here is that if you look at 0 to 1 over n, when you iterate your dynamics, if you think of this gap from 0 to 1 over n to be a hole, and once your dynamics falls into this hole, you close it, and then you ask for what sets don't die. That's this survival set that they're interested in. And that's very much related to f less than equal to n. The other thing, if you're interested in sequences, is instead of the Virahanka Hemachandra Fibonacci sequence, you could try and generalize our example and figure out what happens with constant recursive sequences. I think there's a lot of fun to be had here between the sort of dynamics of algorithms community and the fractal geometry community. So I don't have any conjectures about this, but I have a feeling that those coefficients will be related to important numerical characteristics of the sequence. So after constant recursive sequences, you could try even more complicated settings like holonomic sequences, automatic sequences, etc., etc. There's a lot to do there. Okay, you're like, wait, these are all really airy-fairy. I don't want to study new things. This is going to be too much. Well, here's an example of the simplest Cantor set for which I don't know how to do an asymptotic expansion. So we call it the co-Cantor infinite similarity IFS. So you remember your Cantor set. So you see this Cantor set has, yeah, we're still live. Countably infinitely many gaps, which I'm starting to highlight in blue. And so this co-Cantor infinite similarity IFS is the one generated by these similarity maps. So you just generate as map close gaps onto 0, 1. Okay. So there's infinitely many gaps, just scale the gaps to 0, 1. Those are your generators. So that's your alphabet. And now try and find asymptotic expansions for less than equal to n or greater than equal to n for starters. Here's another countable CIFS for which I don't know how to do it. For those of you who are interested in number theory, you might want to look at, instead of the Fibonacci sequence, another sequence that a lot of people are interested in, the prime sequence. So now look at continued fractions whose entries are prime numbers. We don't know how to do that. We don't know how to say, hey, what's the asymptotic expansion for the Hausdorff dimension of all irrationals whose continued fraction entries are the first n primes. Okay. If you want to challenge yourself to go to higher dimensions, you could try and work out similar expansions outside the conformal setting. So in what's known as the self-affine setting. So this means that you're sort of contracting in different rates depending on in different directions, rather than conformal systems that are basically one-dimensional in the sense that your contraction in all directions are the same. A beautiful example that's not self-affine, is still conformal, but is much harder, is trying to do complex continued fractions. This is a beautiful area if you're not aware of. Check out this paper of Mariusz with two of his collaborators, Chiosones and Lekekman. And okay, this is just the basic idea. You take the Gauss CFS, okay, which you all know. I used to call those G's, now they became U's, I don't know why. You replace the alphabet N with the Gaussian integers, And then, oh yeah, the Gaussian integers with positive real part, because this is an n and that's a z. And then you replace the unit interval, your playground, with this ball in the complex plane. And then you get beautiful fractals. Sometimes people like pictures, and somehow all these one-dimensional fractals are hard to visualize. But if you move up a dimension, you suddenly magically get beautiful pictures. I just want to throw in that the one-dimensional examples are also very beautiful. All right, now I could talk a bit more about some stuff, or we could have questions. I'm open. I think we started a little late, so I'm okay with time, but I don't know. It's Ben and Noel's call, and actually all of your call. Do you want to see some more problems that you could work on, or do you have questions?
Just while everyone's thinking, I have a question I was holding from before.
Yes.
Um, you mentioned that like there's a Bartle book that shows one of the constructions, and there's two Bartle books. Is it the older one or the newer one? It's like
Uh,
elements of the new one is like 2018 apparently. So
it is. I'm trying to find it. Uh, it is this one.
is it oh, introduction. Yes, okay. Got
Introduction to
it.
Real Analysis, and there's another author because Bartle
Yeah,
died and then Sherbert joined and sort of kept the editions coming. So yeah,
okay.
this is the fourth edition.
Got
This,
it.
this is a really cool book. And guess where I learned about it from? When I was an undergrad at St. Andrews. This was where I studied analysis.
Um, so was the question for the group like, would they prefer question time or to see some, what were the other things you proposed?
Yeah, there's some other questions that I could suggest you look at. Um,
We have a vote for being happy to hear more. So yeah, okay,
let's
that's
let's
two
hear some
votes.
more.
That's enough. Yeah.
So all this while we were looking at asymptotic expansions. And so I want to go back to this little 10-year-old kid, okay, Jack Good. He's lying in bed. Remember, he had diphtheria. What was he doing? He was extracting the square root of 2. So I want to go back to Jack Good. And he definitely tried to numerically compute these Hausdorff dimensions of these sets. He was one in a long list of people. And I don't know how much you know about this story, but I think it's fascinating. Okay, so let's go back to f less than equal to n, and let's make it really simple. Let's just look at f less than equal to 2. Now this set is extremely interesting. It's all continued fractions. It's all irrationals whose continued fraction entries are just 1 and 2. So remember, the generators were these two simple Mobius maps. And so Yarnik, in that same paper where he had bounds for the Hausdorff dimension of f less than equal to n, actually had numerical bounds for f less than equal to 2. And Good, in that same Smith Prize winning essay, also computed f less than equal to 2, and he did significantly better than Yarnik. I'm going to skip a lot of history here, but as you can see, these are some of the many people who continued trying to get after the set. And I want you to notice that we've come from 1928 to about 2018, and we seem to have got about a little more than 10 digits. So a big breakthrough in all these methods was then also someone who we've mentioned, Mark Polycott, along with Jenkinson, Oliver Jenkinson, they proved around the same time that they could get 100 digits for this set f less than equal to 2. And their proof is, again, it uses functional analysis, but it uses a few twists. It uses things like zeta functions. Why do zeta functions come up? Because you look at periodic points of the Gauss map. And this is a dynamics community. You might guess that these periodic points grow very fast in n. And so somehow this was the end of the story up to 2018, because Polycott and Jenkinson's methods, like if you said, hey, you can do 100 digits of f less than equal to 2, could you give us 200 digits of it? And they would say no, because it would take longer than, the time it takes for all of us to disappear into a nice little black dot. And you still wouldn't be able to get more digits using this method. So some of the people are pictured here, but several of the people are not pictured here. These are some of the people I would like to call the wizards of dimension computation. And I've not included, of course, Yarnik and Good, whose pictures you've seen. These are ones that came after Yarnik and Good. You might recognize some of them. But what about you? You're actually part of my next slide. I'm hoping that I'm going to have pictures of you on the next slide. And these are the new wizards on the block with, rather than 20th century PhDs, with early 21st century PhDs. But of course, this word early is parentheses. And then these are some of the people who have been continuing the work, and I'll tell you how they could improve on what was on the previous slide. So they can actually do 200. They can do 200 digits of f less than equal to 2 now. So here's the challenge. Here's the problem for you, is pick an n and compute the Hausdorff dimension of f less than equal to n to 2 to the 10 digits in 2 to the 2 hours on 2 to the 0 laptops. Okay, so or a desktop if you have. So I hope you realize that this is way beyond what's currently known. We're very excited when we could go from 100 digits to having a completely new method to give us 200 digits of these. And of course, all of these challenges, I'm phrasing them in terms of Hausdorff dimension, but you could pick these challenges about any dynamical numerical invariant you're interested in. Okay, so it could be the Lyapunov exponent. It could be, right? Don't just think of continued fraction Cantor sets. This is a very broad program. And then this first one was a Cantor space, f less than equal to n. Here are some bare space examples, infinitely generated IFSs or countable alphabet IFSs. And again, this is what's known. So 10 digits is unknown. And here are some references. I did mention that the Polycott-Jenkinson's result that could do 100 digits has been improved. That improvement is in the last last reference, where Polycott was joined by Polly Vitnova, whose picture you saw on the previous slide. Polly is the one with the awesome hat. And they could do now 200 digits. It's a totally different method. No zeta functions or periodic points are touched. Okay, so basic idea of these challenges is, once you have a transfer operator, how are you going to numerically handle its spectrum? This is the broad area in which all these problems can be phrased. So it's just like estimating eigenvalues. It's a tough problem. From a
Oh,
geometric point of view, oh,
Tushar.
sorry. Yeah,
Sorry. No, I just wanted to interrupt with a question from a while ago.
yeah, please.
Sorry. No, someone was just asking, I think, about something you mentioned before. They want to know where the conformity comes into play in your theorems
Yes, it's
before.
an it's an excellent question. Um, so as I said, all my projects are footnotes to Hausdorff dimension, right? So they're all involve techniques. All the techniques that I mentioned today involving the transfer operator boils down to something known as Bowen's formula, or if you remember from a basic fractal geometry class, something known as Hutchinson's formula or Moran's formula. This is for the Hausdorff dimension of, say, like the Cantor set, right? Like, are you familiar with that formula? You take the sum, let me just write it in. Let's say you've got, ah, you know, these are contractions with contraction ratio Ri. So then what you do is you take the sum of Ri to the S equaling 1. And then guess what? You've got an equation, and the Hausdorff dimension is inside that scalar equation. It's S. And so you solve for S. In this case, where your maps are similarity maps, this solves the problem. Now, if you move beyond similarity, you could ask for conformal maps, and there's a version of this formula known as Bowen's formula. So you can look that up in that book by. So this story grows up and is generalized into Bowen's formula. And this allows you, again, to have a formula where you can solve for the Hausdorff dimension using something known as pressure. It's the zero of the pressure function. I'm just saying this because I know a lot of you are experts in thermodynamic formalism or students of thermodynamic formalism. Let me not say experts. No one's an expert. And this is exactly where conformality comes into play. Okay, so Bowen's formula, that whole slide where I had L and Ln, and I said that encoding that the Hausdorff dimension is that delta n, which is kind of like playing the role of S here, is encoded in the spectral radius of that operator being 1. That's another way to phrase Bowen's formula. So that's where it's hiding. So it's a very good question. If, for example, you wanted to try this out with, like, say that the only time I went out of conformal was when I said self-affine. And I talked about Natalia Jurga and Henry Reeves papers. Or actually, yeah, you could have interpreted any of the open dynamical systems problems as one that's not conformal. You're going to need another approach. So yeah, this method of using transfer operators, the way I've described, is about conformal dynamical systems. If you look, so let's say you're interested in self-affine fractals. So, instead of a Cantor set, the next simplest example I could think of are what are called Bedford-McMullen sets. They could be carpets in 2 dimensions. They could be sponges in 3 or higher dimensions. So I have a paper with David where we have a formula, which is a variational principle. So it's like a min-max formula for the Hausdorff dimension of these sponges. Again, there's no, it's a finitely generated affine IFS. And it's much harder. What we know about self-affine is much less than what we know about conformal. But it's very interesting for you, because that means there's work to be done.
Did that help? Or yeah, just ask more questions as they come up. Okay, so then I was saying you could ask the same questions instead of these number theoretic sets. You could say, no, I'm more interested in like Julia sets or like Kleinian group limit sets. And of course, the same problems are there. So you could ask, hey, could you compute 2 to the 10 digits of the Hausdorff dimension of the Apollonian gasket? That's a very favorite fractal of mine. McMullen, back in the day, improving on results of Boyd, this sort of reminds me of Yarnick and Good playing with f less than equal to 2 about 100 years ago. That's where they're at right now. But you could be the first to try and improve these results. So I talked about, I just mentioned a Kleinian group limit set, and I just said Julia set. And so maybe I'll end with saying that all the problems, if you thought conformal dynamics is not rich, and you have to, the problems that you're interested in are more in the affine setting or the non-conformal setting, I just want to show you a way that you can make conformal dynamics extremely rich for you. So there's this famous Fatou-Sullivan dictionary between limit sets of Kleinian groups or Fuchsian groups in 2 or 3 hyperbolic dimensions, and then on the other hand, between Julia sets that are formed by iterating rational functions, holomorphic functions. Now, I loved reading about this dictionary when I was a kid, and I still am amazed by it. And so the big takeaway I want to give you is, instead of thinking of this as a bilingual dictionary, I want you to start thinking of it as a trilingual dictionary. And in between the realms of Kleinian groups and Julia sets, you should think of IFS attractors, or more generally, graph-directed Markov system attractors. And the point is that you can use this middle column to sort of interpolate and solve problems in the other 2 columns. And so whenever you hear a talk about any one of these columns, you should try and say, hey, can I prove a result in one of the other columns? And in some cases, we've not always been able to do this, but sometimes you're able to prove one theorem that would get you results in all 3 columns. And that's pretty exciting when that happens. The last time that happened was in 2017 for me with David and Mariusz. So the big takeaway here in terms of this talks is, whenever you hear something about IFS or a graph-directed Markov system, think about the other 2 realms as well. And this table is taken from our paper that is linked to on the Big Ideas in Dynamics website. We could have talked more about this. The slides say a little, like just a dash about it. There's lots of problems about rigidity that we could have talked about, but I wanted to do something very, very concrete. What could be more concrete than iterating Mobius maps or rational functions, right? Linear fractional transformation. So that's a trilingual dictionary. And then the last few slides I have are about that dictionary. This is a picture of, maybe you can guess who it is. It was an engineer of mines back in 1879. Many of us, have heard of the Poincaré conjecture, but many of us forget that he was a mining engineer back in Caen, in France in 1879. And he was studying these very intricate fractals that were actually initially brought up by Klein and Schottky. And so these are examples of these are quasi-Fuchsian limit sets, if you're familiar with those. I like this slide because it shows you a picture done by Fricke in 1897, and then one done by Charita in 2009. And this sort of shows you this whole story, because Charita was very well known in the field of holomorphic dynamics, but he took some time to code. His code, by the way, is accessible. If you write to him, he will share the code with you if you want to make these drawings. And they're amazing. You can actually move the circles around and see how the limit set changes and zoom in. Mind-blowing programs. Just email Sharita. That's another thing I want to tell you. Often I would just email people and just say, hey, I'm nobody. I know you don't know me, but can you help me out? I'm interested in this thing I read about you did. And just be shameless. And 9 out of 10 times I would get a response. And 1 out of 10, no response. That's fine. Or maybe 9 out of 10 times, if you don't get a response, it's fine too. But just reach out and ask people. So I'm not going to talk about this. So I'm just going to just skip these slides and get to what was one of the main theorems that we proved. So one of this big, what we call a meta theorem, because it's a theorem that allows you to improve results in the fields of rational functions, Kleinian limit sets, and IFS. So it's like one single idea that can be applied in these 3 areas. And that says that, let's say you have lambda be the limit set of a conformal dynamical system. So like one of our IFSs we were dealing with, or maybe a Kleinian group or a rational map. And our result is basically, if lambda is not too much bigger than what are called the radial limit set, that's a subset of the limit set of points that are, radially approximated in some sense. So for example, if the non-radial limit set has 0 Hausdorff dimension, then you have this rigidity between either the Hausdorff dimension is bigger than the topological dimension, or you are a nice manifold. So you're either fractal or you're manifold. If you're interested in that paper and you've started reading that rather than the other paper about continued fraction expansions, and you are like, well, what kind of stuff could we do there? There is actually very interesting problems in that setting. That would be a totally different talk. But I just want to highlight some of them. Our argument is basically studying a notion called rectifiability, which is a notion in geometric measure theory. Let me write down a reference here. Mattila has a new textbook called Rectifiability or Rectifiable Sets. I just saw it at the JMM at the Cambridge booksellers table. Let's just say rectifiability. Cambridge University Press. So you first have to learn a bit about rectifiability. Our whole paper uses rectifiability to prove this theorem. And now you could say, well, how can we extend what you did? Well, there's been an amazing extension of this theory of rectifiability, which was initially done for Euclidean spaces. And that's been extended to the setting of metric spaces, metric measure spaces. And it's done by David Bate. And so if you study Bate's paper, and I'm not saying that's going to be an easy thing to do, you have to be interested in wanting to know more about rectifiable sets. If you do that, then you could take our result, which proves this thing for geometrically finite Kleinian groups, for example. So by the way, a geometrically finite Kleinian group satisfies this condition. The non-radial limit set has 0 Hausdorff dimension. In fact, the non-radial limit set is a countable set of points. They're what are called the bounded parabolic points. And so it's a countable set. So of course it has Hausdorff dimension 0, but Bonk and Kleiner have two papers where they prove a similar rigidity theorem like written above. I like calling this a Bowen rigidity type theorem because it all started with Rufus Bowen's 1978 paper. And so they've got a similar theorem where they extend it to cat -1 spaces. So instead of a quasi-Fuchsian action on, like, say, H3, they can do a convex co-compact action on a cat -1 space. So a dream would be to extend this method to the setting of metric spaces. So can you do it in such a setting rather than like what we did in Hn? And we actually also did it for H infinity, which is infinite dimensional hyperbolic space. I also want to throw a plug out for infinite dimensional hyperbolic space. Most of you, when I was a student, no one ever told me about infinite dimensional hyperbolic space. But now it's a thing, and it's really made a huge impact on math because of the Cremona group and the work of Cantat Lamy. So if you're interested in working in beyond finite dimensions, you could try and maybe think about looking at cat -1 spaces that were not proper and asking a similar question there in that setting. And you know, there's many areas you could work on. I've mentioned a couple of them, like the McMing class group or OutFN or the Cremona group. They're rigidity theorems that, you know, no one knows as yet how to prove in all of these settings. But I think the first very interesting concrete example would be to prove the exact same theorem as above. This one I'm just underlining for the setting of convex co-compact actions on cat -1 spaces. This would be, if you can do this for, Bonk-Kleiner did it for convex co-compact, so you would have to do it for geometrically finite or more generally as written above, which includes geometrically finite actions. So that's, I think, a good place to stop. And thank you for your patience. Ask me questions. Go ahead. Thank you.
Well, thank you for a great talk. Does anybody have any questions? I think we have time for maybe one. Okay, I have a question.
Yeah, you have a question, but I'm just going to repeat that, you know, email me, email Noel and Ben. All of that is totally, I would love to do that. Yeah, but Ben, go ahead, sorry.
So this is a very ill-formed and ill-posed question, but you mentioned that Bowen's equation was part of the reason that you work with these conformal iterated function systems. I think that I've heard, and I might be incorrect, that to deal with these non-conformal, or to deal with some non-conformal things, you can work with a kind of generalization of Bowen where you work with kind of the sub-additive thermodynamic formalism.
Yes.
Is that a possible route to kind of?
Absolutely, I should have said that. Yes, that is definitely a possible route. If you use the sub-additive thermodynamic formalism, though, I don't think you can hit things on the nose. You can get bounds, but if you want asymptotic expansions, that should be fine.
Okay.
I don't think you could do something with that would be analogous to maybe, like, you know, that Fibonacci formula where you've got a convergent series. But again, I haven't thought about it, but it's a great point. Looking at the sub-additive. Yeah, the paper I mentioned about the Hausdorff dimension of sponges, self-affine sponges, that does not use any thermodynamic formalism. So it's a like sort of another approach. But yeah, the subadditive thermodynamic formalism is another way to hit Hausdorff dimension of non-conformal sets.
Thank you. Okay, well, let's thank Tushar again for a great talk. We'll post the slides somewhere where all of the participants can see